Iron is chemically predisposed to react with oxygen. When left exposed, it oxidizes, turning into the brittle orange flakes we know as rust. Even high-grade modern steel requires constant intervention, coatings, paints, and chemical barriers to prevent the environment from breaking it down. But in the center of Delhi, India, there is a 6-ton iron column that has stood in the open air for over 1,600 years. Despite centuries of monsoon rains and modern air pollution, its surface remains dark and intact. It shows no signs of the structural decay typical of iron exposed to the elements. This pillar functions outside the standard life cycle of iron structures, maintaining its integrity through a process that differs from modern metallurgical expectations. The column was forged during the Gupta Empire, a civilization with a well-documented history of metallurgical skill, visible in their stamped silver currency. These artisans worked without the centralized high-heat blast furnaces or the chemical additives that define the modern industrial age. Despite those differences, they produced a material that has proven more durable over the long term than many of our contemporary alloys. Researchers have looked at the pillar's composition to understand the specific engineering choices that led to this result. Its survival is a result of a specific metallurgical tradition that utilized local resources in a way that produced a lasting chemical stability. Laboratory analysis of the pillar has isolated the specific variables within the metal that prevent corrosion. The most significant difference is the level of phosphorus. The pillar's ore contains a much higher concentration of this element compared to modern iron. Smelting with traditional charcoal and wood fires allowed this phosphorus to remain integrated into the iron, rather than being burned off. In modern steel making, phosphorus is viewed as a contaminant and is removed to ensure the metal isn't too brittle. However, in this specific historical context, its presence became the key to the pillar's longevity. The interaction between the specific local ore and the charcoal-fired smelting created a chemical base that behaves differently than the steel we use today. When the high phosphorus iron makes initial contact with moisture and oxygen, it triggers a unique, immediate surface reaction. This reaction creates a compound known as misoite, forming a dense lattice of iron, oxygen, and hydrogen atoms. This layer acts as a physical seal. As the model shows, oxygen and water molecules bounce off the lattice, unable to penetrate and rust the raw iron. Exposure to rain and humidity actually thickens this layer. The environmental forces that typically destroy iron only serve to reinforce the pillar's protective skin. The oxidation process is effectively diverted. Instead of eating through the metal, the corrosion is transformed into a permanent, self-renewing barrier. The pillar's survival is not a matter of luck. It is a demonstration of how a specific metallurgical tradition can successfully utilize the chemical properties of a local environment. This outcome challenges the idea that metallurgical progress follows a simple upward line from the past to the present. The Gupta smiths developed a method that provided long-term protection, achieving a level of durability that modern industries still works to replicate in harsh environments. It raises the question of what other sophisticated examples of early material engineering exist, functioning through scientific principles we are only now beginning to analyze. Technological history is filled with these specialized practices, results of a deep understanding of materials that allowed ancient civilizations to build for a timeline of over 1,000 years.